Hello everyone, welcome to Great Learning. Trees. Yes, we are talking about trees, but this time with respect to Java. Trees play a crucial role when you want to work as a developer because it is an important data structure that will help you crack many interview questions as it has some unique features compared to other data structures. We at Great Learning thought of bringing you this video where I will teach you everything basics about trees, traversal methods, and how to implement all that using Java. Shall we get started? Before we get started, I want to introduce you to Great Learning Academy, a free initiative by Great Learning. You can access over 200 plus courses with 1000 plus hours of free content on trending high demand domains absolutely free. Register now to complete the course and get your free certificate of completion. Check out the link in the description of the video below. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notifications bell so that you don't miss out on any new updates or video releases from Great Learning. If you enjoyed this video, show us some love and like the video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video, any queries or suggestions, and I will respond to your comments. Hello everyone. So welcome to this course Trees in Java. So here we'll try to understand what are trees, what are the different terminologies used in a tree and how is it different or what are the advantages when we try to use tree when compared to other linear data structures such as array and linked list. So let's see the agenda for this course. So this is the agenda which we'll see. So first we will see introduction to tree. We'll try to understand the different terminologies used and the different types. And then we'll go ahead with binary search tree. So we'll try to understand how is it different from a normal tree and what are the advantages of using a binary search tree and why is it so famous. And then we'll try to compare a tree with a binary search tree. We'll try to see the differences among these two types of trees, and then we'll try to understand why you have to use trees when we have so many other linear data structures such as array or linked list. Why should you use trees? Then few operations on binary search tree. So what are the different types of operations which you can perform? And then the traversals, that is the pre-order, in-order and the post-order traversal. And then finally we'll get our hands dirty and implement the Java code for the binary search tree. And then we'll end up our discussion on this particular course. Let's get started then. Let's begin with introduction to tree. So here we'll try to understand what is a tree first and then what are the different terminologies associated with a tree and how is tree different from other data structures. And then with an example, we'll try to understand these terminologies as well and we'll see how a tree, a logical tree looks like. So without a further ado, we'll begin with the introduction to tree. So first of all, what is a tree? So tree is nothing but a data structure. Now, what is this data structure? You might have heard of arrays, linked lists, and all, right? So what is this data structure? So data structure in simple terms, if you want to understand, it is nothing but the method or a way in which you're storing the data, right? So data structure is nothing but the way or the method in which you are trying to store the data. Now tree is a data structure wherein we store the data in a hierarchical form. Now what is this hierarchical format? What is this hierarchy first of all? So let me give you a simple example. Okay, so you have your laptop or smartphone, right? So consider your laptop. So when you turn on your laptop, you have this folder called my computer, right? And inside my computer you have a folder called my music, and here you are storing all your music, that is all of your songs. So my computer, my music and all your songs, right? So this is nothing but a hierarchy or levels, different levels. So it is nothing but your directory structure or folder structure. So my computer, my music and then the songs, correct? So this is forming a hierarchy. Let me take one more example so that it'll be clear for you. So consider a corporate company, any big MNC, okay? So how do they work? So first of all, at the topmost level, they have the board of directors, okay, and then you have CEO, CFO, and CT on the next level, and then you have some managers on the next level, and then finally the M. Okay, so what is the thing here? We are forming a hierarchy: board of directors, CEO, CFO, and CTO, then the managers, and then finally you have the employees. So this is forming a hierarchy, correct? So now with this, let's try to understand again what is a tree. Tree is nothing but a data structure wherein the data is stored in the hierarchical form. So I think with this, the tree definition is clear. What is a tree in simple terms? Next, we do not store the data in sequential order tree. That is, tree is not a linear data structure. Okay, what do we mean by that? We're not storing the data in sequential format. That is one after the other. We also have multiple levels. So as the data is stored in different levels, we can have multiple levels inside a tree. Correct? Because we are storing it in a hierarchical form. So obviously we'll have different levels. Correct? Then where do we store the information in this tree? Okay. So there's something called as node. Okay. So tree can have multiple nodes or a single node, all the information inside this node. So this node contains all the data or the information. Now the collection of nodes collectively, you can call it as a tree, correct? So collection of nodes is a tree. And here again we have few more terminologies like child, parent, and links, which we will cover in the next slide. So these are few important terminologies associated with a tree. So what are these? So we have something called as a root node. We have something called as a parent. Then we have something called as an edge, a child node, a leaf node, and the sibling. Now just by looking at these terminologies, you will not understand what are these. Okay. So what we can do is we can simply go ahead with an example and try to understand these things better. So let's go ahead with an example and try to understand these terminologies and how a tree looks. We'll try to understand. So this is how your tree looks, a logical tree. Now consider the real-time tree, okay, the one which you see out. Okay, so there the root sits at the bottom, correct? Now and then you have the branches and the leaves, right? Now just upside down the real-time tree so that the root comes at the top. That is what your logical tree looks. So here the root sits at the top. Let's start with this example. Now here this is your root node, and then this is your edge or the links, and then we have these two links from node A to node B and E. So now this is your root node A. B and E can be called as the child nodes of root node A. Why? Because look at the arrows here or look at the edges here. Okay, so now root node A is the parent node of B and E. So basically root node A is having two children, B and D. Now let's try to understand what are these siblings. Okay, so look at this. Node F and node G are sharing a common parent node, which is E. So now F and G can be called as siblings. Why? Because they are sharing the common parent. Okay, now C and D are also siblings because they are having a common parent node, which is B. Now node D and F, are they siblings? No. Why? Because they both are not sharing the common parent. So D and F cannot be called as sibling nodes. Finally, what is a leaf node? Okay, now observe here C, D, F, and G, these four nodes. Okay, they are not having any child, correct? They are not having any child nodes. So such nodes which do not have any children, okay, such nodes are called as the leaf nodes. So what are leaf nodes? Nodes which do not have any children can be called as a leaf. So let's start again with the beginning. So here what you see at the topmost is the root node. Okay, so a root node, always remember, doesn't have any incoming leaf. Okay, always a tree begins from a root. Can you see any arrow here? No, right? So root node doesn't have any incoming edges or incoming links. Then root node A is a parent of node B and node E. Then C and D are the child nodes of node B. Similarly, node F and G are the child nodes of node E. And F and G are siblings because they are sharing a common parent, E. And any node which is not having a children is called as a leaf, such as C, D, F, and G. So I hope the understanding of a tree, a normal tree, is clear. So now if you observe here, every node is having two child. root node A, root then node B, then node E. Now, in a normal tree, it is not mandatory to have only two nodes. So what I'll do is, I will draw one more child, okay, and I'll call it as H. Put the arrow. So now, it is not mandatory to have only two children in a normal tree. It can have any number of child nodes. So there is no restriction on a normal tree to have, you have to have only one child, two child, or three childs. It can have any number of child nodes, right? So this is how your tree looks like, a logical tree, and it can have root node, a parent node, a child node, the edges, the leaf nodes. Now, if you look at this part, this is called as the left subtree of root node. Similarly, you can call this part as the right subtree of root node A. So again here you can form subtrees as well. This collectively is called as a tree, and inside that you can have left subtree and right subtree. So with this, I hope the introduction to trees is clear. We'll continue with our discussion on the next topic. Next up, let me introduce you to binary search tree. So here we'll try to understand what is a binary search tree, how is it different from a normal tree, how to construct a binary tree, all this with an example. So without wasting time, let us quickly start with this binary search tree topic. So here, look at these pointers. So the first pointer says binary search tree is a special type of tree. So first, let us try to understand what is this binary. So a binary tree is nothing but a node in a binary tree can have maximum of two child nodes. So that is the name binary. So bi means two. So binary tree means maximum a node can have maximum of two child nodes. So that is the reason it is called as a binary tree. Now here we are learning about binary search tree. So why is it called as a special type of binary tree? And here also a node can have maximum of two child nodes. So how does this binary search tree become special? So look at the second pointer. So here every node, okay, every node is compared. Let me repeat that. So here there is a root node, and then all the values smaller than that of the root node are present on the left side of the root, and all the values greater than that of the root node are present on the right side of the root. So this is what makes a binary search tree so special. How? This we'll try to understand with an example. Now here, as the name says, here the frequent operation which we perform here is the searching operation. We also have insertion and deletion, but whenever you want to perform the search operation faster, so you will try to incorporate this binary search tree in your program. So what we can do is the search operation becomes faster whenever you introduce binary search tree in your program as a data structure. And also it is called as an ordered binary tree. Now why ordered binary tree? Now if you see here, we have some sort of ordering. What ordering? That all the nodes present on the left hand side of the root node are smaller than that of root, and all the values present on the right side of the root node are greater than that of the root node. So such that it comes in an order. So whenever you want to perform any operation. Now let's try to understand all these with an example in the next slide. So now I have listed all the inputs here with a binary search. So how did we get this binary search tree? So what we'll do is, with this list, I'll try to construct this binary tree. So let us understand how we got this particular binary search tree. So now observe here, every node has two childs or zero childs. So it comes along with a restriction that any node in a binary search tree can have a maximum of two childs. So if you observe here, 15 is having two child nodes, 12 is having two child nodes, 20 is having two child nodes, and all the leaf nodes, that is 10, 14, 18, 25 doesn't have any child. So this is how your binary search tree looks like. Now quickly, let us try to understand how did we get this particular order. So now let us consider our first input 15. So the first input in the list is considered as the root node of your binary search tree. So 15 is a root node here. Now what we have to do, go to our input. So what is the next incoming input? We have 20. So 20 should be compared with the root node 15. Why? Because binary search tree is a special tree wherein all the values present on the left hand side should be smaller than that of the root node, and all the values present on the right hand side should be greater than that of the root. If you compare 20 with 15, it is greater or smaller? Greater, right? So what you have to do? Move to the right of your tree. So 20 will be placed here as a right child node of the node 15. Next up, what do we have? We have 18. So when you compare 18 with 15, again 18 is greater. So simply move to the right side. Now compare 18 with 20. It is greater or smaller? Smaller. So what we have to do? Simply move to the left side and place the value 18 here. Got it? Next, we have the input 12. So 12, if you compare with 15, what is it? Smaller, greater, smaller. So move to the left side. So 12 will be placed here. Next up, we have 25. So 25, when you compare with 15, it is greater. So move to the right. Compare with 20, again it is greater. So move to the right, as simple as. So 25 will be placed here. So like this, just compare all the incoming inputs with the root node. If it is greater, move to the right. If it is smaller, move to the left. Next input, what do we have? We have 10. So 10 is smaller than 15. So what we have to do? Drill down to the left. Compare it with 12. Again, it is smaller. Simply move to the left and place 10 here. The last input, what we have here is 14. So 14 is smaller than 15. Move to the left. Compare with 12. Greater. Move to the right. And 14 will be placed here as a right child of the node 12. So this is how you get your binary search tree construct. So this is how I got this particular binary search tree. Now, what is so special about this binary search tree? So like I said, here the frequent operation which we are performing is a search operation. So now consider if I want to search for a value 18. Consider if I want to search for the value 18. Now, what I can do is I can simply compare 18 with my root node 15. Okay. If it is greater, I'll simply move to the right subtree. If it is smaller, I'll simply move to the left sub. Now, what should I do? 18, I want to search. So I'll simply search 18 in my right sub. So this will save half of your time traversing to the left side of the. So you should not at all search in the left subtree, because you know that 18 is greater than that of 15 and all the values greater than 15 are present in the right sub. So you can save a lot of time searching. I'll repeat this. So you can save a lot of time when you want to perform the search operation. So here I'll compare 18. It's not present here. Then I'll move here. Finally, I'll get the value which I'm searching for. That is 18. So this is how a binary search tree can work for you. And this is how it is special as compared to other trees. So next up, we'll have a discussion on tree versus binary search tree. We'll see how these two are different and what are the advantages of using a tree and what are the advantages of using a binary search tree. Now we are in our next topic, which is tree versus binary search tree. So here we'll try to find out the major differences between these two and how do they get along with each other. Let's get started. Now, a normal tree, a general tree, or just a tree. All three mean the same. So do not confuse yourself with these different terms. Now, in a tree, a node can have either 0 child, 1 child, 2 children, or 3 children. It can have any number of nodes. So there is no restriction on how many nodes must be present inside a tree or when you're constructing a tree. Now that is not in the case of a binary search tree. And a tree also does not follow any ordering when you're trying to construct. So there is no arrangement as such that this value should be placed in the right subtree, this value should be placed in the left subtree. You can place that value anywhere, right? And there is no restriction that a parent must have only 2 child nodes, 3 child nodes. You can have any number of child nodes for a parent. Now, let's see how binary search tree is different from a tree. Now, as the name itself says, you can have maximum of 2 child nodes in a binary search tree. Now, you can here also again you can have 0, 1 or 2, not beyond 2. The restriction is maximum 2 child nodes. That's it. Nothing more than that. Now, unlike a normal tree, we have some sort of ordering here. We do follow a ordering in case of a binary search tree, but that is not in the case of a normal tree. So here we have some sort of arrangement in case of a binary search tree. Now consider there is a root node. Now all the values present on the right side or in the right subtree of a root node must be greater than that of the root node. And all the values present in the left subtree of the root node must be smaller than that of a root node. So this is what is followed in a binary search. Now, let me take one more simple example through which you'll understand why binary search tree has an advantage when you're trying to consider search as a major operation. Now, consider you have your normal tree, okay, and you want to search for a particular number in that particular general tree. Now, what happens is you don't know where that number is present, so you have to all the way drill down to the leaf nodes until you find the particular value. But that is not in the case of a binary search. Now what happens here? Now there is a root node. So if the value which you want to search is greater than that of root node, you can simply traverse in the right subtree of the root. If that value is smaller than that of the root node, you can simply traverse in the left subtree of the root. So this makes your search operation faster as compared to a normal tree. So in a normal tree, you have to traverse all the nodes and check if that value is present or not. So that might get your tree search operation little slower than that of a binary search tree. Fine. So I hope with this you have understood the major differences. Now we are in our next topic, which is what is the use of trees. Here we'll try to find out what are the different uses of trees when we compare it with other linear data structures. So let's get started. So tree, as we know, is a non-linear data structure. That means we are storing the data in a hierarchical format. We already know now what is a hierarchical kind of a structure. So now that itself makes a tree a great data structure to perform different kinds of operations. It could be insert, it could be delete. Now, as compared to other data structures, which are linear data structures, say for example, an array or a linked list, where we are trying to store the values in the continuous location, which is one after the other. So a linear data structure has its disadvantages when we are trying to perform operations such as insertions or deletions, right? Now tree comes to our rescue whenever we are facing such kind of a problem. So tree is a non-linear data structure where we are not storing the values or the contents in a sequential format. So we have a hierarchical kind of a format to store the values, which can help us solve a different kind of problems which require the data to be stored in that particular format. Also, when you use tree as a solution for your application or a program, the time required to perform any operation on a tree is O log of n, which is great when you compare it with other linear data structures. Now, when you consider an array or an ordered array, those are considered very bad when you want to perform operations such as insertions or deletions. Why? Because the data is stored in a sequential format. So from the beginning till the end, you have to traverse or search for a particular value to be deleted. So if that value is present at the end of the array, then from the beginning till the end of that particular array, you have to keep on traversing until you find that particular element. But that is not in the case of a tree. Why? We are storing the data in the hierarchical format, and we have different methods through which the insertion, deletions, or search operations can be optimized. But that is not possible in an array as compared to a tree. Also, when you consider linked list, the search operation can be cumbersome. So it can be slow as compared to a tree, because again here we are trying to store the values in a linked list wherein it contains a pointer and a node. So the node contains the information. So we have to traverse so much things here. So tree comes to our rescue when we want to build such applications. So whenever we are not satisfied with the linear data structures for our application or program, we can go ahead with a tree data structure. So that will help us solve many kind of problems when we are building our application or a program. So now we are in our next topic, which is operations on binary search tree. So here we'll try to understand what are the different types of operations which you can perform on a binary search tree. Now here we have these operations which you can perform on a binary search tree. So the first one is insert, then delete, then search obviously, and then traversal such as pre-order, in order, and post order. So let's see the first operation, which is insert. Now assume you have a blank tree. Okay, so for the first time when you're creating a binary search tree, the first node will be the root node, and then you are going to decide based on the binary search tree property whether the next incoming node should be the left child or the right child of the root node. So insert is very simple. So first, if there is no node present at all, the first node will be the root node, and then based on the binary search tree property, you are going to make the next incoming node as the right child or the left child of the root node, and then consecutively you can form the right subtree or the left subtree of the tree. Next operation is the delete. So here in delete there are three scenarios. So let's see what are the three scenarios here. So in delete we'll come across zero child when you have zero children, and then when you have one child, and then it could be that you can have two children. So these are the three scenarios when you're trying to delete a particular node. Okay, so a node which could have zero child, you don't have any problem, you can simply delete that particular node. And then when you have one child, this also will not cause much issue, because you have to just delete that particular node and remove the link. Now the problem is you have to be very careful when you're trying to delete a node with two children. So you have to think which should be the next parent node or the root node. So let me take an example. So suppose I have this particular tree here. So say for example, I have 10 here, I have 8 here, then I have 12 here. Now what I'll do is I'll extend my tree. Let me have one more value here. So let me have 4 here, and let me have 15 here. So now if you want to delete this particular node 10, which is the root node, now what you have to do, which node, either 8 or 12 should be the next possible root node. You have to decide on that. So now if you want to delete the root node 10, which has two children, 8 and 12, now one possible solution is, if you want to make the root node from the left subtree, then you have to consider the highest among the left subtree, which is 8. If you want to make the root node or select the root node from the right subtree, then you should consider the least value from the right subtree. So it could be 12. So that is your delete operation. Then you have your search operation. So the heart and soul lies in the search operation when we are considering the binary search tree. So this is the most frequent operation which we are using, or which we are trying to implement using the binary search tree. And then finally we'll come across the traversal. So traversal is nothing but we are trying to visit each node at least once. So here we'll come across pre-order traversal, in-order traversal, and post-order traversal. Now we are in our next topic, which is pre-order traversal. So here we'll try to understand how a tree can be traversed in this particular pre-order fashion. So let's get started. So here we have to follow some steps or some rules to traverse a tree in a pre-order traversal method. So what are these rules or steps to be followed? So first is, in pre-order traversal, we have to traverse the root node first, and then we have to move to the left side of the tree, and then traverse the left side or the left subtree of a node, and then we have to move to the right side of the root node, and then traverse all the nodes present in the right side of a tree. So these are the steps which you have to follow whenever you are traversing in a pre-order manner. So you have to remember these steps in order to follow this particular traversal method. So what are the different uses and what are the different applications of a pre-order traversal when you are trying to apply it on a tree or binary tree or a binary search tree? So let's try to understand these with an example. But before that, let us try to understand how this pre-order traversal works. So let me take this example. With this example, you'll easily understand how pre-order traversal can be performed on a tree. So at the root node, we have 15. And then on the left hand side, we have 12 as the left child. And on the right hand side, we have 20 as the right child of the root node 50. Now, if you observe, The left side is also called as a left subtree if you have more number of nodes. And on the right hand side, it is also called as a right subtree because we have more number of nodes there. So there also some sort of subtree being generated. So now we have to continuously traverse from the root node until you reach all the leaf nodes in this pre-order traversal. So let's start and try to understand how this particular tree can be formed into a pre-order traversal method. So what we have to do here, first we have to start from the root node. So pre-order traversal, we are always starting with the root node. So 15, what I'll do, I'll make a note of it here. Next, according to the steps, what we have to do, go to the left side of the tree. So this is my left side of the left subtree. So here I have 12 as the left child of the root node 15. Now here again, if you observe, we have a tree here, which is a left subtree. Now this left subtree must also be traversed in a pre-order manner. So here again, I'll apply the same rules. So here I have the left child of the root node, which is 12, and then I'll make a note of it here as well. So according to the rule, root node first and then the left and the right. So now I have made 12 as a note in my list, and then I'll continue to traverse on the left side of the left subtree. So here I come across the value 10. So 10 I have written it here. Now what is remaining here in the left subtree? It is nothing but 14. So now 14 I am listing it down here. So now if you observe, we are done with the root node. We are also done with our left subtree. So we have completely traversed our root node and the left sub. So 15, 12, 10 and 14. This is what we have got after traversing the root node and the left side of the root. Now what is remaining here? The right sub. So in the right subtree, again we have to apply the same rules and traverse this particular right subtree recursively so that we finally get our pre-order traversed values. So now here if you observe, as a parent we have 20. So I'm listing down 20 here, and then we have 18 as the left child of 20. So what is the next thing? Listed down here as well. What is remaining now? The last node is 25. Now list it here. So according to the rules or the steps of pre-order traversal, we have traversed all the nodes in our tree, and this is what we have got here. This is the list which we have got after traversing all the nodes here. Now you might be thinking, what is the use of this pre-order traversal? What are the different applications and uses? So the first and foremost is, whenever you want to replicate a particular tree or create a copy of a tree, you can use pre-order traversal because it will generate the same type of a tree. So that's the first thing. What is the next thing? Whenever you want to count the number of nodes in your tree, you can use pre-order traversal. And the third one is, whenever you want to count the number of leaf nodes, the nodes which are at the end and which do not have any child are called as leaf nodes. So whenever you want to count the number of leaf nodes in your tree, you can make use of pre-order traversal. And then one important aspect of pre-order traversal is, whenever you want to convert an expression tree into a prefix notation. Let me take an example so that you have a better understanding. Now here I'll draw a small tree. So here in my root node I have this plus operator, and on the left hand side I have minus, and on the right hand side I have suppose division. Now these operators also have some child, so let me write A here, and let me write B here, let me write C here, let me write D here. So now assume this is an expression tree which you have got, and you want to apply the pre-order traversal to this particular expression tree. So what will be the output of this particular expression tree when you apply the pre-order traversal? Let us see that. So first what we do, we visit the root node. So I've got the plus here, and then what we do, we visit the left subtree. So here we have the minus operator, and then we have the operands. So we have to traverse what? The left child of minus, which is A, and then we have to traverse the right child, which is B. Now again we are done with our root node and our left. So now we are done with our root node and our left subtree. So now what is remaining again here? The right part. So on the right part, we have the division, then we have the operand C and D. So this is one more important application of a pre-order traversal. You can convert an expression tree into a prefix notation. So I hope with this you had a better understanding of pre-order traversal. Now we are in our next topic, which is in-order traversal. So here we'll try to understand how to traverse a tree in this particular in-order fashion. Let's get started. So in this in-order traversal, what we do is first we visit the left side of the root node and then we visit the root. So this is the difference from the pre-order traversal. So first we visit the left subtree, then we visit the root node, and then we visit the right side of the root. So these are the steps or the rules which you have to follow when you want to perform the in-order traversal on a tree. Now, what are the uses of this particular in-order traversal and how to implement or how to traverse this particular in-order traversal? We'll try to understand this with an example so that it will be more clear for you people. So just look at this example. We have a tree here. Now we want to perform in-order traversal on this particular tree here. So just observe the tree and be with me to understand this particular example. Now at the root node we have 15 and then on the left side of the root node we have 12 and then on the right side we have 20. Now these two are also left and right subtrees as we know. Now where do we start from? Where do we begin from according to the rules of in-order traversal method? Now we have to begin from the left side or the left subtree. So now this is our left subtree, correct? Now here we have to start from 10 because this is our parent node which is 12 and this parent node 12 is having the child 10. So we are going to start our traversal from this node 10 here. So what I'll do, I'll just make a note of this 10 here and then I will move on to the parent node which is 12 and then again I'll make a note of this parent node 12. Then finally I'll traverse to the right child of the parent node 12 which is 14. Then again I'm listing it down here. So now I'm done with the left subtree here, correct? So now what do I get after traversing the left subtree? I get 10, 12 and 14. This is what we get after traversing the left subtree. Now let's move ahead and continue with our traversal operation. Now again we'll go back to the root node. Now our next job is to make a note of this root node here. So I've listed down 15 here because we are done with our left subtree. So the next thing is obviously we have to list down the root node according to the rule of the in-order traversal. So we have listed it down here. What is the next thing? We have to traverse the right side or the right subtree of our tree here. So when we move to the right side, we have 20, 18 and 25 here. So 20 is the parent node which is having two childs. Now what do you have to do? Again traverse in the same manner. So here I'm going to move to 18. So I'm listing it down 18 here. And then again have traversing to the root node and then making a note of 20 here, which is the parent of these two children. Now finally, I'm moving to 25, which is the last value which you're traversing in our tree. So I'm writing it down here as well. Now if you observe, we started from 10 here and traversed all the way to 25 here by applying the in-order traversal rules or the steps. Now look at this list which you have got here. What do you observe here? So if you observe this list, it is in an increasing order, which is nothing but ascending order. So this is one of the important application of this particular in-order traversal. So whenever you apply in-order traversal on a binary search tree, what you get is a sorted output. So it could be ascending order in this particular example, which we have seen. So like this, let me take one more example. What I'll do is I'll draw a small tree here. So let me write minus here and let me draw two children. Let me say plus and then multiplication. And then again these two nodes have child x, y, and this has s and t. Just assume this. Now, if you apply in order traversal on this particular expression tree, what is the output you get? So there are situations when you want to visit the left side or the left subtree first, then the root, and then the right subtree or the right side of a tree. So when such scenarios are required by your application or program, you can choose in order traversal as a solution for your program. Now look at this example. What we'll do is we'll try to traverse this expression tree using the in order traversal steps. So first what we get here is we have to go straight to the left subtree. So here what we see in the left subtree is we see x. Then when you visit the root node you have plus. Then the right child is 1. Now let us go to our root node where we have this minus symbol. And then again we have to traverse the right subtree. So in the right subtree what we have S, we have star, and we have t. I have missed this minus here. So x plus y minus s into t. So this is your in order notation of this expression tree. So you can also apply in order traversal to such expression trees. So with this, I hope you have understood how to traverse a tree in an in order fashion. Now we are in our next topic, which is post order traversal. So here we'll try to understand how you can traverse a tree using this particular traversal method, which is post order. Now here, what are the rules which you have to follow when we want to traverse a tree in this particular manner, that is post order. So as the name says post order, here we are considering the root node, that is visiting the root node at the end. So first we are visiting the left side of our tree or the left subtree first, and then we'll move to the right side of the tree, and then finally we will try to access the root node. So these are the steps which you have to follow when you want to traverse a tree in post order manner. So considering other traversal methods such as in order or pre-order, here we don't have too many applications of this post order traversals. We will discuss those with an example in our upcoming discussion. So now here, considering this example, we will try to apply the post order traversal on this particular tree which you are seeing on the screen. So let's begin with our left subtree, because the step says first we have to move to the left side of the tree. So on the left side, what do we have? We have 12, 10 and 14. So we have to start from the leftmost node here, which is 10. Then we have to straight away go to 14, correct? So look at this list here. First I have noted down 10 according to the rule or the steps. Then I'm visiting the right child of the node 12 here. So I'm also making note of 14. Now what is left in this particular left subtree? We are left with the node 12, which is the parent of these two children. Now finally we will write down 12. So now we have completed the traversal of left subtree with the help of post order traversal. Now next, should we consider 15 now? No. Why? Because next we have to traverse the right sub. So in the right subtree we have 20, 18 and 25. Now again in this right subtree, what we have to consider? So we have to go to the left child of the node 20. So there we have 18. So consider 18 and make a note of it. So next, should I go to 20? No, I have to consider 25. So make a note of 25. So now we are done with the left subtree as well as the right subtree. So we have traversed these both trees of this particular bigger tree. Now what are we left with? We are left with our root node, which is 15. So finally we are noting down 15 in our list. So this is how you are going to traverse a tree using post order fashion. So again, there are situations when you want to consider the root nodes at the end. So your program or your application might demand such that you want to consider the leaf nodes first and then the root nodes. So in such scenarios, you can consider the post order traversal method to your application or the program which you're trying to build or write. Then we also have two more uses. So one more use is whenever you want to delete the nodes of a tree, then you can use post order traversal. And again, we will see the expression tree as an example. How do we traverse an expression tree with a post order traversal? So that you have a better understanding of this particular method. Now consider this example. I have this time, let me take star here, the division operation. Then let me take division operation here. Then let me take the addition operation here. And then I will consider S, R, and then A and B. Now consider this expression tree here. And if you have to apply the post order traversal, what would you get? You would get the postfix notation of this particular expression tree. So how do you get that? Let's see that. So now what we have to consider here, we have to consider the leftmost tree. So when we consider the leftmost node here, we have S. Then we have to go to where? The right side of that particular subtree. So we have R there. Then consider the division operation. Next, what you have to do? We have to go to the right side of the tree. So there, what do we have? We have plus as the parent node, A and B as the child nodes. So now, what we have to do? Consider the left child, that is A, then move to the right child, which is B, and then finally we are going to write plus. And then finally we are going to go to the root node. There we have the multiplication operation. So this is how you can also draw a postfix notation using an expression tree. So these are few uses of the post order traversal which you can use in your program or application based on the requirements. So I hope with this you have understood the post order traversal and you will use these in your applications. Now we are in our next topic, which is Java implementation for binary search tree. So here we'll try to implement the code for various operations in a binary search tree. So let's get started. So here we have the implementation of binary search tree. So if I have to start typing and explaining, then it'll take a lot of. So what I've done is we have the implementation code here. Don't worry, I'll explain the code line by line so that you have a better understanding and all the methods implemented will be explained in detail. So let's start with our first line of code. So we have a class here, public class demo bst1. Then I'm creating an inner class here, public class tree node. Now whenever you are writing a program for tree, binary tree or binary search tree, the first thing is you have to create the tree first. So how to do that? First we need a root node, we need a left node, we need a right, and then the data or the information which you want to store inside your tree. So for that reason, what I've done here is first is int data to store the information inside the nodes. Then I have created the left node and the right node here of type tree node, and then we have a constructor here to initialize the members here. So this dot data is equal to data will initialize the data, and this dot left and this dot right is equal to null will initialize these two with the null, because initially the tree is empty. So whenever it is empty, we don't have anything to fit into our left or right. So that is the reason we are inserting null at this particular point here. Also, we are left out with our root node. So that part is also declared here. Now again, when the tree is being created for the first time, we are going to insert the root with also null. So that is done here. So far we have created a tree. We have created the left and the right node, and root node is initialized with null because it is empty initially. So this part is with our tree creation. Now next, what are the few more operations? So let's start with insert, because once you've created a tree, the next thing is if you want to perform other operations, first the values should be present in your tree, right? So what we'll do is we'll create the insert method. So this is our insert method. Just observe this statement here. So insert tree node root comma int the data to be inserted. So we are passing two parameters here. One is the data which has to be inserted, and the other is we need the root node as well. Now, what is the first scenario when it comes to insert operation? So when we have insert, first we are checking if the tree is empty. If the tree is empty, then the first value should be inserted in the root. Correct? Now for that, what we are doing is observe this statement. If root equals null, then root is equal to new tree node. We're passing the parameter, the data to be inserted. So this statement will insert the first value in your tree inside the root node. If the tree is already present, if you have already few values or few nodes in your tree, then based on the binary search tree rules or the constraints, you have to properly insert the values. So what are those rules or situations? Let's try to understand. Now, if the value which you are trying to insert is smaller than that of the root node, what you have to do? You have to insert that particular node as the left child of the root. Correct? So for that, what is the code or line of code? So if root dot data is greater than the data to be inserted, then insert that particular data as the left child of the root node. And how to do that? Root dot left is equal to insert root dot left comma data to be inserted. So here you are calling this insert function recursively to insert the value as the left child. Now, what could be the other scenario when you're trying to insert? So other scenario could be that the value which you're trying to insert is greater than that of the root. What do you have to do at that point of time? You have to make that node as the right child of your root node. Correct? So for that, what is the line of code? Else if you're checking if root dot data is smaller than that of the data which you're trying to insert. What do you have to do then? Simply assign that to the right side of your tree. How to do that? Look at this particular line of code. Root dot right is equal to insert. Again, we are calling the same function recursively. Insert, but this time it is root dot right. And the value which you are trying to insert through the data to be inserted parameter. Clear? So I hope with this the insert method is clear. We're passing two parameters, the data to be inserted and the root. And first we are checking if root is equal to null. If yes, then simply insert that into the root node. If we already have some content in our data, then check and go with the binary search tree properties. Insert the data or the nodes appropriately in the left or the right child. And then finally, we will return our root. So this completes our insert method. Now what is the next thing? We can also implement the search method. So how does a search operation work in binary search tree? First, we are checking if the value is present in the root node or if the root node is empty. Nothing is there in our root tree. That is the first situation. Next possibility is you have to compare the search value with the root node or compare it and check if it is smaller or greater. If it is smaller, search in the left subtree. If the value is greater than that of root node, search in the right subtree. So this will solve your problem halfway through because you're not searching the whole tree here. Correct? Let's try to understand the code here. So this is the method search tree node root int data to be searched. Again of type tree node. The first condition here is we are checking if root equals null. What if nothing is present in your data? Then what are you trying to search? Correct? So we are trying to check that here. Or what if root dot data is equal to, that is double equal to data to be searched? You are comparing the value present in the root and the value which you are trying to search, if both are equal or not. If yes, then we are going to return the root. As simple as that. So now we are done with our first scenario. What could be the next possible scenarios in the search operation? Same according to the binary search tree property. If the root dot data is greater than that of the value which you are trying to search, then what you have to do? Simply search for that value in the left subtree or the left side of your binary search tree. So for that, what is the line of code? Call the search method recursively. Search root dot left comma data to be searched. So this will search for the data on the left side of your binary search. Similarly, what if your value is not present in the root, is not present in the left side of your tree? So what is left now? Only the right part or the right side of your tree. And how to perform the search there? Simple. Again, call the search method recursively, but this time it is root dot right, and pass the one parameter data to be searched. So this will search for the value recursively on the right side. So all these methods are written recursively because this will solve the problem of lengthier code. So if you write iteratively, the code will be simple, but it will get extended. So here the code is according to the concepts of the binary search tree. It is very easy to understand if you have understood those concepts very well. You will not feel the program is lengthy or anything. So now let's continue. So this time let's discuss one of the traversal methods, which is in order traversal. So what happens in order traversal? First, there we are trying to traverse the left subtree of our tree. Then we'll visit the root node. Finally, we'll visit the right side. So this is what happens in an in order traversal. And how to write the code for that? It is very simple code, just 4 to 5 lines, as you can see on your screen. So first we are going to check if root equals null. That is, what if nothing is present to traverse, correct? So we are going to check if root equals null. Then we are going to simply return nothing. What is the next thing? Next, we will call our inOrder method recursively and we'll traverse to the left side of our tree. How to do that? InOrder, pass the argument root.left. So this will recursively visit all the nodes from your left subtree. Similarly, after traversing the left subtree, we have to visit the root, correct? So now we are printing out the value present in our root. Then finally we have to traverse to the right. So for that, again the same line of code, but this time the parameter will be root.right because we want to traverse the right side of our tree. So with this, we have completed the in order traversal method as well. What is the next thing? Our driver program or the main program. But before that, just see here, we also have few wrapper methods for the methods which we have seen so far. So insert method is being called in the wrapper method insert into tree. Similarly, search tree is a wrapper method wherein we are trying to call the search method. And inside in order traversal, we are calling in order. Now, why is this written? So that it will enhance the readability of your program. So anybody looks at your program, he's able to understand by the code that, okay, this is the flow of the program. From here, we are going to this particular method. So this will increase the readability. Now, let's move to our driver program or the main method. So here we are creating an object or an instance of a class, which is BST. And then we'll also need another two variables to take the input for our tree, correct? So we are also using the scanner class here. So scan is equal to new scanner system.in. So scanner is a class through which you can take the input from the keyboard or any other input device. So as we need input into our tree, we are trying to take it from the user. We're trying to make it a little bit of interactive program. So next line, system.out.println. We are asking the user how many numbers he wants to give as an input to the binary search tree. Now here n is equal to scan next.int. So this will take the input for the n, which is the number of values to be inserted into our binary search tree. And then we're asking the user to enter all those n numbers. Then we have a simple for loop here, simple for loop block, wherein we are continuously taking those inputs. So for that, num is equal to scan.nextInt. So this will give the input into the variable num, and immediately we are calling the method bst.insert into tree, which will insert the value entered by the user into our tree. Next, we are simply displaying a message once we are done with inserting. Tree insertion done. And then we will try to perform a search operation. So we are asking the user enter the number to be searched. We are storing again that in n. And this time we are checking if the number entered by the user is present in our tree or not. And how we are doing that? If bst.search tree of n, we are passing the parameter n here, is not equal to null. So whatever value the user inserts, we are checking if that value is present in our tree or not. If it is present, then simply we are going to display the message number found. Else, we are going to display the message number not. And then finally, we will also try to print the contents of our tree in order traversal method. So how to do that? just call the method. So bst dot in order traversal. That's it. So this will print your tree in the in order method. So what we'll do is we will quickly run a program and check if you are getting the proper out. So enter how many numbers. So let me give 7. So we'll quickly let me give the values 25, 25, 7, 12, 15. One more value. So 21. So tree insertion done. Now we have to enter the number which we are trying to search in our tree. So let me search for 21. So the number found and the in order traversal is also being printed on the screen. So in order traversal, if you observe, it is in ascending order. So in order traversal will always print the contents of a tree in a sorted manner. Now what we'll do is here I have shown only in order traversal. Correct. Similarly, you can also implement pre-order and post-order with the same line of code, just a little bit of changes if you know the traversal properties correct. Now, what we'll do is we'll also try to implement pre-order and post-order traversals. So for that, what I'll do is I'll simply copy paste these contents. You don't copy, you please type it. Here, due to time constraint, I am copying it. So pre-order, let me print the pre-order. So here I'll make it pre. Okay, pre-order traversal, and then I'll also create a wrapper method for the same. So it will be pre, and this will also be pre. What else? The main part. Now, what happens in pre-order traversal? First, we are going to visit the root node, then the left, and then the right. So accordingly, change the lines of code here. So first, we are going to visit the root. So this statement, I will put it in the first line, and then we have our left and the right. So are we done here? Yes. So we have written the code for pre-order, we have written the wrapper method also, and we are printing it here as well. So let me make the corrections here. Yes. So this is a pre-order traversal. Similarly, let us create the post order as well so that you can see the examples for all types of traversal methods. So post order traversal. So here it will be post. Similarly, we'll create the wrapper method as well. What I have to change here? This will be post. This will be post. Now, so in post order, we are visiting the left first, right next, and then finally the root. So now what I have to do, I have to simply move this line at the end, and this will be post order. That's it. Those are the only changes which you have to make. So if you have known these traversal methods, it's very easy to implement. Now we are done with everything. Yes. So let's quickly run and check. Let me insert few numbers this time. Let me insert 5. So 25, 22, 1 and 7. Tree insertion done. Enter the number to be searched. So this time let me insert a number which is not present in our tree. So let me check with 36. Number not found. If you can see this, number not found. In order traversal, it is printing it in ascending order. Pre-order traversal is also being printed, and post-order traversal is also being printed. So we have performed the insertion, creation of a tree, insertion of a tree, searching for a value in your tree, all types of traversal methods also. So I hope with this you have understood all the methods which we have seen so far in our example. So from the beginning, we'll quickly check out. So this was our tree construction. After this, we had a method to insert the values into our tree, and then we had a method for search operation. Then we created the method for in order traversal, method for pre-order traversal, method for post order traversal. Now what are the changes here? It's just the rules which you have to follow, or the steps which you have to follow for performing these traversals. So all the lines of code are same, but you have to follow the steps for the specific traversal methods. And then we have our wrapper methods here as well. And then finally, we have our running program, driver program, our main program. So I hope with this you have understood the implementation of binary search tree using Java. As we are in the end of this course, let's try to summarize and understand whatever you have studied so far. So first we saw introduction to tree and the different terminologies used in tree, how a tree looks and why is it so important. And then next we went on to understand the binary search tree and why is it so special and the working of a binary search tree with an example. Then we compared a tree with a binary search tree and saw which one is more important and what is the use of trees. That is our next topic. So what are, when we compare a tree with different data structures, what are the uses of trees over other data structures? And then we also saw a few operations on binary search tree, correct? And then we went on and moved to the traversal part. So traversal, we understood pre-order traversal, in-order traversal, and how a post-order traversal is done. And then finally we also saw the implementation of binary search tree in Java. So with this, I hope you have understood this particular course properly. Thank you. I want to introduce you to Great Learning Academy, a free initiative by Great Learning. You can access over 200 plus courses with 1000 plus hours of free content on trending high demand domains absolutely free. Register now to complete the course and get your free certificate of completion. Check out the link in the description of the video below. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notifications bell so that you don't miss out on any new updates or video releases from Great Learning. If you enjoyed this video, show us some love and like the video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video, any queries or suggestions, and I will respond to your comments.